Hey all, sorry about the late upload today. I got to doing a couple of other things. I'm helping one of my old students write a grant proposal, and despite the pandemic, that sort of stuff is not off. So I decided to commit the first half of the day to that, and it kind of took me a little bit longer than I wanted to. So here I am. Um, Fortunately, what we're going over today is, in my opinion, super simple, really short, not even going to be as intense as last time. Um, so we should be able to get through this in about 30 minutes, give you some time to go out and practice. I'll keep updating you guys with emails about when I think quizzes are going to be, um, how I think we're going to use the conferencing tool next week. If we're going to use the conferencing tool next week, I'm kind of open to suggestions there. Um, Hopefully, after another chapter's worth of material, you guys will kind of get an idea about whether like meeting with me online, not face to face exactly, would be to your benefit. So just let me know about that one way or the other. And then for the rest of the day, I'm going to work on getting your midterms posted by tonight. With the move to online, it just takes me longer to grade. I told you guys this for a week now. So most of your assignments are going to take about a 2 week turnaround. It's just going to be the case. Your quizzes and stuff I should grade relatively quickly. In fact, I still think I have your chapter 7 quizzes to enter. But for your second exam and for your final exam, it's going to take me some time to get those grades up. So just be patient with me, and I'll try and pay it back to you guys in terms of more generous grades, hopefully. Um, but today we're going to do chapter 9. So if you happen to have the PowerPoints um, uh, up, you might want to refer to that one. We're going to start with slide 1. We're going to go through this one more or less in order. Just to let you know, for the next couple of classes, we're doing chapter 9, very quick. Chapter 11, the reason I'm skipping chapter 10 for the time being is chapter 9 and chapter 11 have very, very similar tests, whereas chapter 10 is not as similar. So chapter 9 is going to be an intro to all that, and I'm going to be teaching you the simplest of the 3 t-tests today, which is the most similar to the z-testing stuff that we learned in chapter 8 that we just came out of. I'll probably also post a video on Tuesday, maybe tonight, going over the midterm, just so you guys can get some feedback about how you did. I'll try and keep, I have like an Excel spreadsheet with your names on it and each question and how many points you got, so I can kind of refer to that if need be. But I obviously can't like do track changes or anything because you guys sent it to me in different formats. So as far as the midterm goes, but I just want to make sure that in transitioning from chapter 8 to chapter 9, you guys understand how they relate. Because if you understand how to do chapter 8 stuff, chapter 9 is a breeze. You're talking about one additional step. So let's refer to the notes real fast. Just going to go to the second slide here. And the first thing I want to lead with is a little bit of a paradox. So I've been telling you guys all semester since we started that when you do science, when you do statistics, you don't know anything about your population. However, for the last few chapters, at least chapters 1 through 8, we've assumed that we knew the population mean and the population standard deviation. In other words, it was given to you by the problem as something that we know. To make that work, you guys saw a lot of examples from your book that used IQ testing, that used the SAT, and you might have thought, why am I seeing so many of the same sorts of problems? Well, the reason is those are only a few of the times where we actually do know the population parameters, standard deviation and mean. When you don't know those, they have to be inferred from the sample, hence inference testing. That's where this comes from. So chapter 9 is on what's called the single sample t-test. Now, the test that I taught you in the previous chapter, chapter 8, was the single sample z-test. So as you can imagine, they're going to be very, very similar. In fact, there's only a couple of changes. One change involves the new table that you're going to use to look up critical values, and it's going to be very similar to the chi-square table that we looked at earlier this week in terms of you're just looking up the critical values. You're not looking up p-values. and how they relate to specific t's. No, 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 no. You're going to use your degrees of freedom, which is to say your sample size, and you're going to use your alpha, and you're going to look up a critical value, and you're going to compare those two. When you do it in SPSS, which I'll show you later in the semester, you're just going to be given a p-value, and you're going to make a determination based on that p-value. If it's less than 0.05, you reject your null, plain and simple. So it's pretty straightforward. Another thing that you're going to have to do is you're going to have to calculate your standard error of the mean from sample standard deviation. How is this different from Chapter 8? Well, in Chapter 8, you were given population standard deviation, and you use that to calculate standard error of the mean. That's a very easy process. When you have to calculate it from a sample, it could be a little bit arduous, depending on how big your sample is. We're going to do a couple of simple examples today, probably one, just because I'm going to be limited by board space. That will show you, how this can very easily be done by hand. My preferred method of doing this, if I were doing this, would be to either use Excel if I was really in a pinch, or if I had, ideally, a computer with SPSS, I would do that. I have SPSS installed on my computer, and again, I do plan on doing an SPSS tutorial with you guys, at least for how to run the tests, but I'm not going to make any of that mandatory because I know not everybody has it. I will, however, show you guys how to read outputs, because you will need to know how to do that for your final exam. So we'll leave all the Chapter 9 SPSS stuff for the side for now, and I'll kind of just show you how to do it by hand and show you how the test works. So that's the paradox. All throughout the class, we've kind of assumed that we know what our population parameters are. Now we're in real-world statistics where we don't know them, and we actually have to infer them from our sample. Conceptually, it's not that hard. It's just the math can be a little bit, I would say, tedious. It's not even hard math. Okay, so I'm going to hop to the next slide here. So in doing this, in adopting a more inferential-based approach, we're going to change our distribution. Now, we're not talking about the z distribution. We're talking about the t distribution. And the t distribution has some aspects to it that are very, very different from the z distribution. In fact, to kind of lay this out there, you might want to skip to slide 7 real fast and look at this kind of infographic, right? So here is how the t distribution changes as a function of your degrees of freedom. Now, what you guys might be noticing there, you've got 3 humps. Those are all t distributions. Now, you might say to yourself, well, Drew, how can a distribution change its shape? The z distribution is a fixed shape. Yes. The t distribution is not. The t distribution changes as a function of degrees of freedom, which is to say sample size. So that red hump there with the degrees of freedom equaling 3 is actually n equals 4. The blue hump, degrees of freedom equals 6, is actually n equals 7. It's always one more. Your degrees of freedom of infinity, well, that's still infinity. So I want you to see what happens when your degrees of freedom changes. So let's take degrees of freedom of infinity, for example. That's about as normal a distribution as you're ever going to see. That, in fact, matches the z distribution perfectly. How do we know this? Well, if you look at the x-axis where it says t critical, look at the cutoffs for 0.05. Again, we're just kind of assuming this is 0.05 here, but we have a pretty good right to make that assumption given what the cutoffs are. 1.96 in black. Those are identical to the ones we use when we're doing a z-test at 0.05, right? Now, let's see what happens when we reduce our degrees of freedom, and reduce it pretty substantially, in fact. When you reduce it all the way down to degrees of freedom equals 6, you notice that your distribution becomes more platykurtic, right? It's flattening out. And as such, the critical values that represent your alpha of 0.05 are being pushed further out into the tail. So instead of having negative and positive 1.96, you have negative and positive 2.45. If you flatten it even further to degrees of freedom equals 3, well then negative 3.18 and positive 3.18. So what does this mean for us? This means that the lower your degrees of freedom are, in other words, the smaller your sample size is, the harder it is to find statistical significance. And this is one of the ideas that gives us this logic that a higher sample size is ideal in statistics. Right? Not only are the results more reliable, but you're also producing more powerful statistical tests. You can actually use a slightly lower criteria if your sample size is comparably high. Now, while we're on this slide, normally I wouldn't do this early, but let's refer to the t distribution table. Excuse me, I'm going to sneeze. No, I'm not. Let me just grab my book. So if you refer to page 575, you'll see the t-table. And again, you're going to like this. It's a one-page table. It is nothing like the z-distribution in that it goes on for several pages. So let's look at some of the values that we have in front of us. So let's take degrees of freedom of 3, for example. Where does that number come from, that negative 3.18 and that positive 3.18 as your cutoffs? Well, it's pretty simple. Line up 3 on your degrees of freedom on the left-hand side of your chart, and then scroll across to 0.05. Now you'll notice along the top row, there's 2 rows. One says proportion in one tail, the other one says proportion in 2 tails combined. If you're doing a 2-tail test, logic dictates you're going to use proportion in 2 tails combined, and you're going to look at 0.05 if your alpha is actually 0.05. So we're going to do that. So 3, and then lining up 0.05, you'll see that our cutoff there is 3.182, and that's where that number comes from. Make sure you're lining it up correctly because it's easy to get mixed up. For 6, if you do the same process, so we move down to 6, we move over to that same column, and there you have it, 2.447, which is about 2.45. So that's where that comes from. Now, if you scroll down even further, staying in that 2-tailed combined column, you'll notice that once you get to degrees of freedom of around 30, your critical value is going to hover around 2, and it's pretty much going to stay there until you get to infinity. I mean, then it's going to gradually go up from 2 to 1.99 to 1.98, and eventually you're going to hit 1.96, which basically means, what does that mean for us? As your degrees of freedom increases in your sample, your t-distribution starts to resemble your z-distribution, period. In fact, as your degrees of freedom approaches 30, you're pretty much in z-distribution territory there. Now, that doesn't mean that you can use a critical value of 1.96 positive or negative if your DF is 30, but it means that your cutoff is going to be pretty close. And so you're kind of shooting for the same number. Hopefully that makes sense to everybody. I would kind of stare around the table, look down that one column, and start to recognize these patterns because it'll help you understand what's going on. Normally I don't advocate staring at a table. It's mostly a tool, but it can actually teach you a little bit. And those little graphs on top can be very helpful in determining what those 2 rows on top mean. Okay, so I'm going to backtrack in the PowerPoint just a little bit to slide 4. So that's one major change for us. The other major change is that we're now going to be calculating standard error of the mean from a standard deviation for a sample. What are the implications of this? Absolutely nothing. We do it the same way. The only difference is the standard deviation that we plug in to find standard error of the mean is no longer the population standard deviation, it's the sample standard deviation. So we just changed the way we write the formula, but the math is the same. It's identical. The crappy part about this is we actually have to calculate standard deviation. So like bust out your chapter 4 notes because we're going to be calculating standard deviation. I'm going to pick some easy problems that allow us to do that quickly. But let me show you what the new formula looks like. It's on that slide. But I tend to call this one, in chapter 8, we wrote it like this. Right, sigma sub n, just sigma over the square root of n, standard error of the mean, right? Ring a bell? Now we're going to write it like this. SD sub m equals standard deviation for a sample over square root of n. Same deal. That's simple. And remember, sigma and standard deviation are interchangeable, as long as you're going from a population to a sample. So you use this when you have a sample, you use this when you have a population. Everything we do t-testing wise is going to be a sample, so you write it like this. The only difference is this number comes from an actual inference from the standard deviation from your sample. This one comes from the problem. In other words, it's a known value, right? So that's what we're going to be using. So that's going to be our new standard error of the mean, right? You can also write it like, the way to do it in APA style, the way to write it in APA style is SEN. Okay? So it's the same thing. All right? I'll erase that before we do our next problem. But, so hopefully so far so good. Nothing drastic changing. Let's go back to the PowerPoint and see what else we've got to go over. So then the T equation itself. So like, how do we actually find our obtained statistics? So remember, I differentiate between the two statistics of an inference test. There is statistic obtained, statistic critical. If statistic obtained exceeds statistic critical, you reject the null. If it doesn't, you don't. You fail to reject the null, right? So in chapter 8, we had z obtained, which is the z that we calculate from our math, and z critical, which comes from the table. Here we're going to have t obtained, which we calculate, and t critical is going to come from the table on 575 that I just showed you. We compare, and then we're done. Pretty straightforward. So the equation for this particular test. Let me talk to you guys about when you would use the single sample t-test, because it's actually one of those tests where one of the values in question doesn't have to be a mean. So usually, let's dissect the chapter 8 test, the z-test, right? It was z obtained equals sample mean minus population mean over standard error of the mean, right? Single sample t-test is sample mean minus something over standard error of the mean. So more or less the same. It's just going to be a matter of what that something is. So when would you use the single sample t-test? I use a couple of examples. The one I usually do in class when I have access to SPSS for you guys is I usually go around the room and I say, hey, how many hours did you sleep last night? And I punch all the data into SPSS for each one of you, including myself. And then I say something like, look, the Surgeon General recommends that people our age, assuming we're all part of the same demographic, get roughly 7 hours of sleep per night. That's a recommendation. It's not a mean. It's just a number that we wish to compare a sample mean to. And we can use this t-test to do that, right? Another instance of when you could use this test is, let's say you, for some reason, know the population mean, but you don't know the population standard deviation. There are some instances where that would be the case. So that second number could be a mean. So if you look at the equation that I used on slide 5, you'll see I did m minus mu over SD sub m. That indicates that that second value is a mean, but it doesn't have to be. So you could write it like that, or another way that I like to write it sometimes is m minus c over standard error of the mean, right? Or SD sub m. You can write it that way too. In which case, well, what does c stand for? It's just a point of comparison. It's any number you can think of that's worth comparing something else to. It's that simple. I like to use the Surgeon General recommends because while that number is not an average, it is an ideal, and there might be some research baked into that number that you want to compare a sample to. I mean, you could say the same thing for, the Surgeon General recommends that you eat X number of vegetables, right? We'll do some examples from the book that are probably more creative than the ones I just thought. But that's basically how it works. And then the math itself is completely identical to the z-test. Completely identical, right? So this is really, I mean, if chapter 8 felt comfortable for you guys, this is going to be just as easy, I think. Moving on to slide 6, I just want to bring up this concept of degrees of freedom again. Degrees of freedom, or DF as it's often going to be abbreviated, for right now for you guys, typically means your sample size minus 1. So n minus 1. So if I were to do this in class and there were 24 of us, our degrees of freedom would be 23. That's simple. When do we use degrees of freedom in these calculations? Well, we use them at 2 points in time. One, when you're looking up your critical value from the table, you need to know your degrees of freedom. And two, you guys will remember from chapter 4 that when you're calculating sample variance to find sample standard deviation, you divide by n minus 1. So you're going to use that number there. So once I calculate the sums of squares for our classroom, rather than divide by 24, which is the number of you that there are, at least in one of my sections, I'm going to divide by 23. So we use this number. So that's, if you see DF pop up, that's what that means. Now just keep in the back of your mind, DF is going to mean different things later on in the course. But for now, it's n minus 1, at least as it relates to t-testing. Okay, so hopefully that's really clear. So slide 8 kind of covers what I talked about when you would use this test. By the way, just as a brief aside, with each of the tests that's coming now that we're actually moving into the territory of like real world tests that you guys will actually use someday, um, I'm going to try and bring in more design elements to the class and kind of explain how these tests work, what kind of studies you would use them for, how common are they, what are some notable examples of research studies that you might know of that have employed these designs, just so you guys get a sense of that. You'll see that with next chapter in particular, because chapter 10 and 11 talk about two different t-tests for different types of research designs. One, a dependent sample, and the other, an independent sample, or between and within subjects, as you guys know it. So we'll talk about that and what that means. And that's really what's on slide 8 there about, single sample t-test. When do we use this guy? Okay, so then it flies right into the steps. And your hypotheses, most of this stuff is not all that different from the z-test. So rather than use this kind of like Mickey Mouse example that I have here, I'm going to pull one from the book to give you guys some context about when you would use this. So if you want to follow along and try this with me, I'm going to do it on the whiteboard behind me. We'll do that. I'll let you know what number and what page. Let's find one that I like. Since I'm not giving you your SPSS project, I can probably give you all of the problems that I would have otherwise just assigned you. Let's see. If you're going to practice this right, you really want to grab one that has raw data. Oh, these are ugly numbers. Ugly, ugly numbers. Rats. Okay, well, I'll tell you what. I'll make one up. I'll do like I just don't want to have to, mess with decimals on a whiteboard since I'm not using SPSS. I'll kind of do a reimagined version of the how many hours did you sleep last night sort of problem. So imagine this. So imagine I have a sample of 5 individuals, and I want to see how many hours they slept for the previous night. Or I guess a better way to ask this question would be, how many hours on average do you as an individual sleep per night rather than last night? So again, we're going to roll with this idea that the number of hours slept is recommended to be 7. So I'm going to call my comparison mean C equals 7. Now again, there is nothing stopping you from writing that as mu. If you happen to like that version of the equation, totally fine. I just like to hammer home the point that that number does not have to be a mean, whereas in the case of most other t-tests, it is. Here it isn't. So however you want to write that. So that's our starting point. So let's say I take 5 individuals, and I ask them, on average, how many hours do you sleep per night? And these are the numbers that I get. So let's say we get 6, 4, 4, 14, 6, and 5. So that should be 25 if I did my math correctly. Yes. So there you go. I don't know if you guys can see that. Right. So that's my raw data, right? So first, step 1 here is, what do my hypotheses look like? Pretty simple. My null is going to state that my sample mean equals 7, or my sample mean equals my mu or my c or whatever. You don't have to actually write the number that c or mu represents, but you can. And my alternative is going to be that it doesn't equal. We're going to do this two-tailed. So if you sleep a different number of hours a night versus 7, this test will capture it. Okay, so that's step 1. I'm not going to write the hypotheses on the board because, again, I don't have a ton of space. And I'm going to need that for calculating the next couple of things. So what should you do next in this case? Now, usually when we're doing the z-testing, we're just plugging numbers in. Now we have to do a little bit of our own math. So the first thing we actually need to do is calculate our sample mean. So if you're following along at home, I told you this adds up to 25, and I don't have you guys to check my math, so I'm going to just double check. That's 14, 20, 25, 1, 2, 3, 4, 5. Good. So 25 divided by 5, m equals 5, right? Easy. So step 2 in the books. In fact, I will write over here m equals 5. So now I have the whole top part of my t equation built up. I know that my t obtained is going to equal 5 minus 7, which is to say that my sample mean differs from my point of comparison by negative 2. Is that a lot or a little? Right? We have to calculate standard error of the mean to tell us that. So we're going to do that. Bring it back to chapter 4, right? So first step, difference scores. We're going to subtract out 5 from each one of these. We're going to get 1, negative 1, negative 1, positive 1, and 0. Well, at least these numbers are going to be low, right? Square those numbers because we have to eliminate the negatives. 1, 1, 1, 1, and 0. And then we add them up, and that's our sums of squares. Okay, so doing fine. Next step would be to find sample variance. Again, I tend to break down variance and standard deviation into separate steps. You can do it all at once, but I like you guys to kind of digest the idea that you can treat them as separate numbers because they are, and you can use one and not the other in certain contexts. So the way we would do this for a sample would be our variance, SD squared, is our sums of squares, which is 4, divided by 5 minus 1. Why 5 minus 1? It's n minus 1, so our sample is 5 things minus 1. So that's going to be, well, I did a better job keeping these numbers nice and easy than I thought. 4 over 4, our variance is 1. Now to go from variance to standard deviation, you just take the square root. Remember, this is variance, it's SD squared. You're looking for SD. So let's take the square root of 1, and shockingly, it's 1. So there's our standard deviation. Now we're not done yet. There's one additional step we have to do. Remember, we have to find our standard error of the mean, so we need to plug all of this in. So we're going to do SD sub m equals, right, 1, which is our standard deviation, over the square root of n. Not n minus 1 now, n. So that's 5. Now, I do not have, let me just real quickly. Oh, go figure. See if I can have my phone. This is so stupid. Bear with me, guys. I'm gonna have to make a mental note too. There we go. So it's going to be 1 over 2.23. Okay, so which is 1 divided by 2.23. 0.45 if you round. It's going to be 0.448. So 0.45. So that is our standard error of the mean. So now we can build out the t equation in its entirety. So t obtained equals sample mean, 5. Point of comparison, 7 over 0.45. So that's negative 2 over 0.45, right? We all agree on that. 4.44 repeated. So our t value is 4.44. Now, normally, I would have a distribution drawn up there with my critical value in it, ready to either reject or accept my null hypothesis. I'm out of space, so I'm going to erase a little bit, mostly the raw data, and draw that in there so you guys can see what we would do now. Remember, we're going to assume that this is two-tailed 0.05, but we haven't looked up a critical value yet, so we need to do that. while I erase the board, why don't you guys look at 575 and see if you can find it before I do. Okay, so remember, our degrees of freedom here is going to be 4 because there's 5 individuals in our sample. We're doing a two-tail test at 0.05, so we're going to use the proportion in two tails combined 0.05 column, and we're going to get 2.776. So negative 2.776 for the low tail, positive 2.776 for the high tail. What did we get? Well, we got 4.44. Where does that fall? Oh, it was actually negative 4.44. Not that it's going to affect the test, the outcome. But it would be over here. Negative 4.44. And then we would reject, or no. I don't know if you guys can see that I did it in red, but so 4.44 gets graphed in over here, well beyond the rejection region. You reject the null hypothesis. So what does that actually mean? Well, it means that your sample differs from sleeping 7 hours per night, which is exactly what your alternative hypothesis would state in this case. So that's pretty straightforward. So that's how you do it. I mean, it's really, if you think about it, hopefully maybe after the midterm you practiced a couple more z-tests. If you didn't, that's okay. But maybe go back and do one of these versus one of those to just try and get a sense of the differences. Remember, here you're calculating standard deviation and your sample mean. In z-test problems, they're given to you. So, there's really no such thing as ugly numbers because you're not doing a lot of arduous math. So the rest of the PowerPoint kind of walks you through how to do this. It actually walks you through how to do it with the sort of Mickey Mouse example that I gave you on slide 8. So if you want to follow along with that and do that as practice, that's fine too. But that's basically it for chapter 9 stuff. I do want to plug a couple of problems that you can do for practice. I wouldn't do them here now because they would probably take longer than they're worth. And I haven't vetted the numbers to make sure that there's no decimals, but they may or may not be okay. So in the chapter 9 problem set, I can tell you the ones that I usually give for the SPSS project, which you can do by hand. They're just going to take you slightly longer than they otherwise would. You can try numbers 22 and 23. I would do 23 first because the answer's in the back of the book. See how you do. They're bigger numbers, but if I had to guess, it looks like they're going to average out to a whole number, so that the different score finding might not be so hard. That's why I'm so picky about it. If you get a mean that's a decimal, finding your different scores is a lot more challenging, as is taking the square root and all of that stuff. So, I like to go with single-digit numbers if I can. It's just easier when you're doing it by hand. And, if there's enough fanfare, I can show you guys how to do this in SPSS sooner rather than later, just so you can see what that looks like. As it stands, I was going to wait until we finish t-testing and then kind of do a one kind of day tutorial of, well, how do I do this in SPSS? And then how do I read the outputs? Because that is the stuff that I'm going to make you kind of responsible for on your final exam. I'm just going to send you the outputs. Like, I'm going to do the analysis for you, and you're just going to read it and then write your results section. So that'll go pretty well, I think. There's no way you can get the numbers wrong, right? So, yeah, so that's it for me today. If you guys have any questions, shoot them to me in an email. Again, so for Tuesday, I'll touch base with you guys before we actually, before I commit to anything beyond the lecture. Like I said, I might try this conferencing tool thing. Maybe we'll do problems. I don't know. I don't know if I'd do it before lecture or after lecture. Maybe I get the lecture posted early and then we do it during class time, because I know that, my first section, you guys have the 2 o'clock time slot open, and my second section, I know you guys are open at 3:30. I also know that you guys have lives and that you're probably struggling with a lot of these adjustments. So I don't want to hold you to just like you guys didn't hold me to having lecture up promptly at 2 o'clock today, I don't want to hold you guys to a time that you're not going to be able to make. So obviously any conferencing that we do would be optional, but it would just be for extra help. Now what I will do for the quiz, so I do have on Tuesday, there is going to be a chapter 15 quiz. It's not a live quiz in the sense that I'm just going to send it to you early in the day. All you have to do is send it back to me by the end of the evening. It's going to be one problem, one chi-squared test, probably the goodness of fit test because it's the easiest one to do. Normally would take you 15 minutes to do it in class, and you're going to have the whole day to do it. Oh, and it's open notes. So it shouldn't be that bad. And you can just send me your responses in the body of an email. If you want to do it pen and paper and then scan it, take a picture of it, and email it to me, that's fine too. I'll try and grade them as quickly as I can too because they're quizzes, and by then your midterms will be done. So apart from posting the lectures, I won't have much else going on. So yeah, all right, that's pretty much it for today. If you guys need anything from me, don't be afraid to shoot me an email, please. I've heard from some of you some really lighthearted responses too, so I'm glad some of you guys are coping really well. Hopefully everybody is. It sucks that we're not doing this in person. But again, like as usual, if you have any requests for video, you want to do more problems, that's fine. I'm trying to keep these videos shorter because it takes me more time to upload them when they're longer. The video from Tuesday took almost an hour to upload. Like YouTube is no joke with longer videos. This one probably won't take nearly as long because it's about half the time. But yeah, I just want to make sure that all of this is digestible and it's discrete. So like, here's Drew's here's Drew's lecture on chapter 9, done, end of story. You don't have to worry about it spanning multiple videos. So, if there's one topic you're not clear on, you can just fire up that video and rewatch it. You can rewind me back, listen again. Honestly, if you don't need the visuals, you can just listen to the audio. That's okay too. I think for some of the math problems, it might be helpful to watch it unfold behind me. But I know a lot of you guys took statistics before, and if you did, you definitely saw this test. So yeah, but that's it for me today. Let me know if you guys need anything. All right. Have a wonderful weekend. It is Friday, right? Yeah, it's Friday. Try to keep your heads screwed on and try to keep busy. All right. Bye, guys.